Professor Land has formal qualifications in architecture and in city planning. He is a researcher of international renown. He is at the Illinois Institute of Technology, and he directly leads research groups in both the College of Architecture and in the Aerospace Engineering Department at the Institute. So if I could please welcome Professor Land to the stage. Very interestingly, one of Peter's, Peter is very, very experienced in wind in relation to our industry, but Peter was also telling me about his passion for ice yachts. 150 miles per hour, is that right?
Up to
150 miles per hour, these things. Now, this is a level of experience, and it's a very interesting thing. I hope that you can incorporate a little bit about your experiences of that and how that relates to the work in our industry. Professor Peter Land.
I don't want to come over as a playboy, so I'm not talking much about my yachting experience, but as a boy I was brought up on a sailing boat, and I've been involved with sailing boats all my life. And since I came to the Midwest, almost 30 years ago, I've been very active in racing ice yachts on the Wisconsin lakes. In fact, I gave up 2 weekends to come here, and I'm missing probably the 2 last weekends of the ice boating season. But the ice yachts are a fantastic platform to study wind dynamics and wind flow, and with the new materials of extremely efficient ice yachts and steels, new stainless steels for the runners, extraordinary performance is obtainable with these remarkable vehicles. Until about 1936, the ice yacht was the fastest vehicle devised by man. There are photographs of the big ice yachts racing the locomotives up the Hudson River in the 1930s, and the ice yachts were the fastest. And then about 1937, the small lightweight aircraft came into being. They went faster than both locomotives and ice yachts. Anyway, I had this passion for many years in this field. Now, I was going to read a paper tonight, actually, which I prepared for this, but I decided against it. It's too boring. So I'm going to go over 1 or 2 main issues here before we look at the slides, which I'm looking forward to doing. In a certain sense, I'm throwing down the gauntlet to my friends from RWI here, because I think you've missed some important approaches, but we'll see about that later in a minute. But the basic idea, now just a few words about what I do. I run 2 research-based studios, design development groups at IIT. One is in long-span structures and types, and the other one is in tall high-rise structures. The basic idea is, how is this coming over all right?
I think everybody can hear well.
Terrific. The basic ideas I'm pursuing is an energy autonomous built environment, sometimes widespan, sometimes tall, with developing buildings which generate electrical energy for their own needs and possibly for export. This means buildings equipped with wind turbines, photovoltaic arrays, and other energy generating systems such as concentrated solar power, which I regard very highly. Our current work is concentrated mostly upon wind turbines on high-rise structures, though I'm also got a lot of ideas on the other fields as well, which we put a little bit on the rear burner because I wanted to get moving on the wind turbine work. So I just recently received a grant to do final refinements on the ideas about shape and form we've already got. And in this area, I'm cooperating. Just started a very interesting cooperation with the Aerospace Department at IIT. So wind turbines on high-rise structures. This means tall buildings or clusters of tall buildings which are shaped to accelerate and focus wind flow onto turbine rotors mounted on the buildings which drive electrical generators. This is the whole idea of the building being clustered and shaped and formed to do these two things: increase the wind flow velocity over curved surfaces, and then focus this accelerated flow onto the turbines of the two types. We have prepared several design proposals over the past few years, and I said recently funds have been obtained to evaluate these proposals and possibly develop others in collaboration with my aerospace friends at IIT. Now, international work in this area is gaining momentum as petroleum resources decline and pressure to develop non-polluting renewable alternatives increase. Several initiatives have recently begun in Europe to develop tall buildings with turbines, but almost none in the USA. The IIT initiative was started by me almost 10 years ago, actually, and is continuing more recently in collaboration with the aerospace people. I think we compare very favorably with the other global initiatives at this time, particularly in project concepts and accumulated data and knowledge. Some of the people, I just mentioned a few names. There's a group in Stuttgart who's doing some work, and there's a man called Stankovic, he's actually an Englishman in spite of his name. He's based in London and doing extremely important work, but there's really nobody else. Now, another very interesting thing is that our data resources include information on the European projects, commercially available wind turbines, and the Stanford NASA Global Wind Survey. That's our sort of Bible for generalizing on wind velocities at 92 feet above grade, which, by the way, is the standards established by this study, because most turbines are about 92 feet from grade to center of the hub. Another very fundamental and very interesting study is which recently came out of Germany. Germany has more wind turbines than any other country. However, a recent German government study indicates that electrical power from wind is more expensive than conventional sources. The study includes onshore and offshore wind farms. Now, this wind energy is expensive, partly because wind technology is in its infancy. However, more important is that wind farms are generally located at considerable distances from where electrical energy is used. Therefore, significant current is lost in transmission, and long-distance transmission infrastructure is very, very costly. These are two very important reasons for energetically pursuing the generation of power at or near the point of use. A tall building or an ultra-tall building can be considered as a mast, generally much taller than a conventional mast, supporting a horizontal axis turbine. Tall buildings may penetrate constant, undisturbed high-velocity air stream, which represents a considerable untapped power source. Technical challenges exist, as you'll see in a minute, but they're not insurmountable. Buildings and structures need to be shaped and turbines developed specially for this context. I just happen to have this slide here because I wanted to, because we're working in new types of structures, in some cases shaped because of wind flow and turbines and so on, but we're also developing a range of geodesic structures and other configurations independent of the wind turbine issue. There's a couple of projects here which we did something like eight or more years ago. I've also been fascinated by the totally triangulated structure and how you're going to change stiffness and then where you should apply the loads in this type of structure. And we did a lot of work on this, and we solved a number of problems. Firstly, we developed a type of triangulated equilateral structure, and the key challenge with this is how do you load this exoskeleton? How do you load it? The best place to load it is at the nodes. Now, and not on the inclined column. You can attach the edges of the floor plates to the inclined column to help the columns to not buckle, but you don't really want to put any substantial loads on these members. So we've applied the loads at the nodes of these inclined columns. If you look carefully, you can see there's a hanger coming down here, and it goes all the way down, and it stops there, not there, it stops there. So all the perimeter plate loads are transferred to these nodes and distributed neatly throughout the exoskeleton. We thought that was an important breakthrough for this type of structural concept. And then energy-wise, this is 80 centimeter, 80 to 1 meter double skin facade here, and in that cavity there is a swirling landscaped band, following some of the ideas of Ken Yang, and the air is guided through the cavity of the double skin and swirls around the building. In this fashion. Now this would be this is a scheme for temperate climates, Chicago specifically. This would be the temperature build-up in the wintertime. The air swirls around the facade, guided by the inclined louvers inside the double skin facade, which by the way also contain the photovoltaics, which drive the fans, which encourage this air movement. And so it will be, in the wintertime, it will be, in the wintertime day, the shutters at the bottom of the cavity are opened, which permit the hot air during the winter solstice to swirl around, and when the sun goes down, the whole cavity, the whole building is encased in a jacket of hot air, and it's closed off at the night, in the night, and that will stay with that temperature for some hours. We've calculated. During the summertime, you want to shed the accumulation of hot air in that double skin facade. So you open these ventilators, which quickly evacuate the hot air every four stories. Now this shows the photovoltaics on the spandrel panels outside, and also these are the angled louvers, which will also have photovoltaics on them at a decent angle to the incoming solar radiation. You can see some of the bracing inside there. Well, this is some of the many types of experimental structures we're developing. Now, getting to what I want to talk about in some detail tonight now is this concept of wind turbines on tall buildings. The whole challenge is to shape the building and have a conception for the building which does these two things, which enables the rotors to focus the airflow to receive the airflow and to work as efficiently as possible. And the biggest challenge is it's very easy to develop take a conventional high-rise structure and tack onto it turbines of any sort. And it's also easy to design a structure which works when the wind is predominantly runs one or two directions. But the real challenge is the omnidirectional concept, And here you see one example of several which we've been working on. It has four corner towers where the principal office space is located, and also what I call flying atria, which enables you to communicate between these four corner columns. This is the section through the flying atria, the corner columns with the main office space and the turbines. Now the thing here is that these turbines, this shows how the variable airflow direction anyway. The turbines are suspended in the center of this space here by side stays. This is now the yachting technology comes into play now. These are side stays which are attached to the structural nacelle of the turbine with all this equipment, and that's the principle of it. These side stays have motorized end anchors, which you see here, which engage with rack and pinion device bolted onto the top cord of the triangular torque-resisting truss here. So these side stays can rotate and turn the nacelle enclosing the gearbox, the clutch, the brake, etc., so that the blades of the rotor are always perpendicular to the incoming wind front. This concept is totally omnidirectional. Of course, you have got a variable pitch blades here, so you can adjust the wind velocity accordingly. Now, this is another concept of the same idea. These are the flying atria. This has 3 supporting corner columns. This is the plan here showing the corner columns with the elevators and fire-rated structural nose-shaped form here. This shows the idea of the wind flow being omnidirectional, being squeezed through this central area, and the wind turbine here. Now, this is a different type of support system entirely from what I showed you before. This is the section with the flying atria and the wind being squeezed through, driving 2 turbines. 4 turbines. No, wait a minute. There's one that's two turbines. This shows the way the wind flow goes through the diagrid of the suspended flying atria. Now, this is you can't see too well maybe, but this shows how the central support column, airfoil in section, rotates and enables the turbine in its nacelle to rotate 360 degrees. So we've got 2 concepts here: a side-stayed turbine housing and the column-supported turbine housing. Now, this is another, by the way, each of these schemes will have about between 8 and 12 drawings. I'm just taking out 1 or 2 to get the flavor of the work. This is another scheme, it's a lens-shaped building, not unlike Sobeck's post tower, and it has turbines located on the narrow edges of the platform and diagrids back and front as a steel building. There's one very interesting thing about this: the turbines. This is the rotor of the turbine, and these are ailerons which can rotate to guide the wind flow over the rotor of the turbine at the most beneficial angle of attack. This shows the rotor here with this little alternator and gearbox at the bottom. This is a turbine made by Windside in Finland. It's an odd. Now the other side, this shows the wind flow streaming, and there's a fluent CFD analysis here showing how the wind accelerates over the corner of the platform very considerably. This is just a set of diagrams here to show how the wind streaming is affected by forms of different type. Now, this is another idea where we've been working on. It's a tripod arrangement of huge structures, by the way. And this is a downwind turbine, 2-bladed downwind turbine now being developed in this country. It has the advantage of being tending to be self-yawing. There's a knuckled just outside the hub, where the blade of the turbine meets the hub. There's a knuckle joint, and since the turbine rotor is downwind, these blades with the knuckle joint can deflect and shed the wind and reduce the terrific pressure on the blades. Downwind turbine self-yawning. Now, there's one thing I forgot to point out. All these proposals will have wind sensors top-mounted on each concept, so that data from the sensors then fed into a computer, and the computer will send the signals to take load off the turbine, or to rotate the turbine, or whatever it has to do. These are simply plans showing how this. Oh yes, this has another very nice feature: cascading vegetation over the floors inside the towers. So the air comes into the building at these points, and then feeds through this cascading vegetation before going into the office or residential space, thereby cooling the incoming, on a summer's day, cooling the incoming air and purifying it. Now this is another idea. This is another idea which has a waveform exterior glass, double-skin glass skin bolted onto the concrete facade, and you can just see the ripple effect here. And the idea is that we locate these windside type rotors in the valley of the waveform, where the wind accelerates very substantially. It's a well-known phenomenon. So the brackets coming out from the facade of the building, and this rotor, which is shaped like the fit turbine from Finland, and pushed into the valley of the skin. So above, I think it's above the something like floor number 8 that the rippling effect begins. By the way, these little circles here are a type of window developed by an architect in Munich called Ingenhoven. It's a very nice window. It's operated remotely and electronically. There's a glass disc which pushes in and out from the facade. Now, another feature, in this particular scheme, we built in a number of features, probably too many, but the top part of the bottom part down here, the glass is eccentrically placed on the cylinder of the building, so that on the south side you have about a 2-meter solarium. So on the south side, the air in the wintertime can be heated up, and then during the day, and then at night when the sun goes down, you can open these concertina doors, and the hot air then goes back into the apartment. You can see how the cylinder is eccentrically mounted in this plan. I think this might be my last slide.
Very interestingly,